Right, this Edpuzzle video is going to be about exponential functions and an introduction to it anyways. All right, so exponential functions are everywhere in the real world. Albert Einstein is known for saying that compound interest is the most powerful force in the world, and that is coming from someone who's split an atom. So you can see the impact that exponentials have, okay, in the real world. In science, you probably studied them through half-life in either chemistry or biology, but they affect our loans, okay, how our money grows. So they're everywhere in our life. And we're going to take a look at it, a little introduction today. All right, so let's talk money. What if you invest $100 in the stock market and it earns 10% every year? So what is happening to your money? So you have $100. It earns 10%. So 100 times 10%, change 10% to a decimal, 0.1, right? That equals 10. You earn 10 bucks. Do you earn 10 bucks the next year? Do you earn 10 bucks every time? What happens to that 10 bucks? So if it was called simple interest, you would just earn 10 bucks every year. And then that interest never earned you money. But what happens in real life is that 10 bucks gets added on to the 100. So now you have 110 bucks, right? And then the next year you get 10%. And now you earned 11 bucks instead of 10. And so now you have $121 and so on. So this is growing exponentially. So another way to look at this, okay, is if I take the $100 and I multiply it not by 10%, okay, but I want to figure out how much I'm going to have in here. I'm going to multiply what we call by a growth factor, right? And that's going to be 1.1. Okay, this is my growth factor. So if I multiply by 1.1, that 100%, takes care of the original 100 that I added the 10 back onto. So this would be 110. So I don't have to get the 10 and add it on. All right. And so if my money is compounding every year, right, and I want to know what it'd be in 2 years, right, what am I doing? I'm taking the $100 and I'm multiplying it by 1.1 twice. Right? Is there another way to write 1.1 times 1.1? That would be 1.1 squared. So 100 times 1.1 squared. Right? And if I want to know how much money I would have after 3 years, right, it'd be 100 times 1.1 times 1.1 times 1.1 3 times. And so again, I could write that as 100 times 1.1 to the third. So there's a pattern. N years, right? I mean, 100 years. I'm not going to write 1.1 100 times, right? So if it's n years, I'm just going to write 100 times 1.1 to the n, and then now I can figure out any year. If it's the 20th year, I just plug in 20, right? 100th year, I just plug in 100. All right, so I am repeatedly multiplying by 1.1. We know this as a geometric sequence. We used to call it a common ratio. All right, and so this is what we have here. This is a geometric sequence, the amount 100 to 110 to 121. Okay, that is a geometric sequence where I'm just multiplying by 1.1 every time to get the next number. All right, so my common ratio would be 1.1. So this is the power of compound interest, right? It's going to grow and grow and grow. Once your money grows, now that money starts to grow. So eventually it starts to grow really fast. All right, so let's do a little review of our geometric sequences. So we have explicit formulas, right? When we by definition of a sequence always starts at the first term. All right, and so when it starts at the first term, we're going to use the first one here on the screen. Okay, f of n equals f of 1, the first term, times r, the common ratio, raised to the n minus 1 power. All right, this n minus 1 power, that's kind of like an h that's being shifted one spot to the right because we're starting at the first term. The other one, which we're going to start seeing a lot more now, okay, is when we start with the zero term. So the zero term would be f of 0 times r to the n. So we don't have to shift it over one spot to the right because we're starting at 0, so we don't have to shift it at all. Right? This would be our y-intercept. So we study these geometric sequences. So the question now is what is r? R is the common ratio. It's what you're multiplying by every time to get the next number in the sequence. All right, and so in this problem right here, this is the exact same problem we just looked at. The money's growing by 10%, right? So, but if you don't know that, we didn't know it because we didn't do the previous one, how can I figure out that 10%? All right, and so what you do is you divide, right, the second number in the list by the first number in the list, right? The first term by the zero term. And then you divide the second term by the first term, and you see what that equals. So if you do 110 divided by 100, you're going to get 1.1. If you do 121 divided by 110, you're going to get 1.1. Right? If I do 133.1 divided by 121, I'm going to get 1.1. Right? It's always 1.1. So it's growing by the same every time, by the same growth factor every time. And that growth factor is 1.1. So our R is 1.1. So if I asked you to write an explicit formula, okay, for this geometric sequence, okay, if we use this one, the f of 1, right, our formula would be 110 times r, which we just found was 1.1, raised to the n minus 1 power. Right? But more commonly, we would say, okay, what are we starting with? Starting with 100. All right, so that's my zero term, right? That's where my bank account was before a year passed, right? So if I wanted to use f of 0, it would be 100 times 1.1 to the n. These are the exact same, they're equivalent equations or functions, all right? Again, one's using the first term, okay, after 1 year, the first term, and then one's using the zero term, right, before any time has passed, right, but they're both equivalent. All right, 1.1. Notice how this money is getting bigger every time. Okay, notice how this number is bigger than 1. It's going to be very important. All right, so same thing here, but now we have, okay, a value of a car. So as you guys know, value of a car is going to depreciate after you buy it and drive it off the lot. So, right, when you buy the car for 20 grand, okay, after the first year it's worth 18,000, second year it's worth 16,200. What is it depreciating by? All right, and so we've got to figure that out. So we've got to do our math where we divide. So we'll go 18,000 divided by 20,000. Now notice, right, that's less than 1, right? And so if you do that, that's going to be 0.9. And we just check to make sure that's the same. And let's do one more. Let's do 16,200 divided by 18,000. And that is also 0.9. So this is going to have that common ratio of 0.9. Right? So what is it depreciating by? Okay, like the last one, okay, the growth factor was 1.1, but we knew the money was growing by 10%. All right, so the rate was 10%. The growth factor is 1.1, but the rate was 10%. And here, the growth factor, or in this case, really the decay factor, because it's going down, is 0.9, right? So what is it decreasing by every year? And that's 10%. So this one's decreasing by 10%, which means it's decaying by a growth factor of 90 or 0.9. So R equals 0.9. All right, so if I wanted to write an explicit formula, again, using f of 1, okay, it would be 18,000 times 0.9 raised to the n minus 1, or using f of 0, right, the original value of the car, would be 20,000 times 0.9 to the n. So both of those explicits would work very well. All right, again, we're calling this 0.9 here the decay factor. We're calling the 0.1 the growth factor. All right, we knew them, right? In terms of R, we call them, it's another word is common ratio, right? What's the common ratio? 1.1, 0.9 would be the common ratios, but we're going to try to be more specific if that common ratio is growing or decaying. All right, so you're going to have an opportunity right now here in the Ed puzzle to answer these two questions. Okay, write the explicit formula for the geometric sequence below. Okay, so for the first one, okay, 3, 6, 12, what is it growing by? So this one's a little bit more obvious, right? You're just multiplying by 2 every time, right? 6 divided by 3 is 2. 12 divided by 6 is 2. So my explicit formula, I'll do both of them here, right, is 3 times 2 to the n, right? My common ratio, my growth factor is 2, right? And my zero term is, or my, excuse me, my n minus 1. This is the first term. Okay? And then if I wanted to do the zero term, okay, I would have to go 1 before that, which would be 3 over 2. So 3 over 2 times 2 to the n. All right, so when you're using a sequence and it starts with the first term, it's easier to use the f of 1. All right, but when you're given f of 0, it may make more sense to use f of 0. So it really depends on what you're given. All right, now do question 2. All right, on question 2, we got to find out what the common ratio is. And so in this case, it looks like I'm dividing by 4 every time. 4 is not the common ratio, right? The common ratio is what you're multiplying by. So that means if you're dividing by 4, you're multiplying by 1/4. So the common ratio is 1/4. Okay, that's my decay factor, is 1/4. So f of n, we're going to use f of 1 here. So 64 times the decay factor, 1/4, raised to the n minus 1. All right, and if I wanted to use the other one, okay, with the zero term, what would come before 64? It's 4 times bigger than 64, that's 256. It would be 256 times 1/4 raised to the nth. And those are your explicits. All right, so now that we've reviewed some geometric sequences, okay, let's make the connection to exponential functions. All right, so we're going to be looking at the parent function first. Okay, the exponential function is y equals b to the x. All right, so b, okay, is the base, x is an exponent, and there's restrictions on b. All right, b can never be negative. Right? If b was negative, this would be considered an oscillating function, because if b was negative 1, if I said y equals or negative 2 to the x, all right, and then I plugged in 1, right? What is 1? Let's make a little table of values here. If I plugged in 1, I would get negative 2. If I plugged in 2, I would get positive 4. If I plugged in 3, I would get negative 8. If I plugged in 4, I'd get positive 16. So this is neither growing nor decaying. It's oscillating. It's going from negative to positive, back to negative, back to positive. The next one's going to be negative. Right? So that graph is going to just be all over the place. It's not growth or decay. All right, and so B cannot be negative. All right, B can't be 0 because 0 to the n power is always 0, so that'll just be a straight line. And it can't, same with 1. 1 to the any power is 1. So our restrictions on B are base, right? It has to be positive, okay? And it has to be between 0 and 1 or greater than 1. All right, and so between 0 and 1 over here, so 1/2, okay, 1/4, 3/5, whatever, any number between 0 and 1, it's going to be a decay factor. It's less than 1. So when you square it or you cube it, it just keeps getting smaller and smaller and smaller. So this is what a decay function looks like. It's going to get smaller and smaller and smaller, but notice how it never gets negative. There's no matter what I raise the power to, it won't make it negative. Right? And when b is bigger than 1, 2, right now it's doubling, it's growing. Okay, anytime b is bigger than 1, you raise it to the power, it's going to grow. So this is our growth function. So you can see it's kind of growing nice, and then it almost becomes like a straight line eventually going up. That's how fast it's growing, and that's why compound interest is so powerful. Eventually, once it gets big enough, it's going to start growing so much upon itself that it grows really fast. Okay, the vocabulary word again, B, we call it the growth or decay factor, right? When B is bigger than 1, it's the growth factor. When B is between 0 and 1, it is the decay factor. Right? It's the same thing that we called the common ratio prior to this. All right, so these are our parent function. We're going to look at graphing. We're going to pick a value for B, and we're going to go ahead and practice graphing it now. All right, so we have an exponential function here, f of x equals 2 to the x. All right, so 2 is our b. That is our growth factor. All right, and so we need to make a table of values. So we start plugging in numbers and seeing what shape this is going to be. All right, so when I plug in -2, right, what is 2 to the -2nd? All right, so hopefully remember this. We just did a unit on properties of exponents. So a negative exponent doesn't make it negative. It means the reciprocal. So it's 1 over 2 squared, which is 1 over 4. All right, so when you plug in -2, you get 1/4. All right, when you plug in -1, you get 2 to the -1st, which is 1 over 2, so 1/2. Plug in 0. Anytime you plug in, raise anything to the 0 power, it's 1. 2 to the 1st is 2. 2 squared is 4. You could have just started multiplying these by 2. It is a geometric sequence when it's in this form. Okay, there's no shifts or anything like that. So we could just multiply these by your growth factor. All right, so I have these points here. So if I plot these, so 2, 4, 1, 2, 0, 1, -1, 1/2. Okay. And so you can see this curve is happening. And what do I need you guys to understand? Like over here, this graph will never go, even though it's always decreasing, it will never go below 0. No matter what number I plug in. Right? If I do f the -1 or f of -100, 2 to the -100th is still a positive number. It's just 1 over 2 to the 100th, which is a number really close to 0. Okay, but it's never going to equal 0. So this graph over here is just going to hug the x-axis, never go below it, okay, and eventually start to come up, and then it's going to start to grow really fast, right? If I did 3, it would be all the way up at 8. 2 cubed is 8. So you can see how fast it starts to grow. And that would be what our exponential function looks like. Now, what we like to do is we like to identify that point, that line where that graph will never go below. Right? In this case, it's just the x-axis. We draw a dashed line there. That line is called an asymptote. Okay, we learned about that when we graphed rational functions. So we've seen that word before, right? It's going to control our end behaviors. All right, so if I said, what is the left end behavior? So as x goes towards -infinity, right? We're going to say the left end behavior approaches 0. It's going to approach that asymptote. Can't go below it. What would my right end behavior be? My right end behavior is positive infinity. So just a quick little review on that, right? As x approaches -infinity, that means left end behavior. My y approaches 0. As x approaches positive infinity, so as x is really big, the right end behavior, now it's going up forever, y approaches infinity. All right, so there's our graph. So now we go to domain and range, okay? So our domain, all right, you can see it doesn't matter what x I plug in, I'm going to get an answer. X could be -100, I could get an x could be positive 100, I get an answer. Right? X always exists. So it's all real numbers. So -infinity to positive infinity. My range though, right, my y values are obviously restricted by this asymptote. The graph will never go below it or never equal it. right? So it's going to get really close to 0, but never equal. So the range is going to be from 0 to infinity. And 0 is going to be in parentheses, not a bracket, parenthesis, because it never actually equals 0. All right, so there's my domain and range. This is an exponential growth function. Right? This is bigger than 1, so it's growth. All right, let's look at one more example. So now we have 1/2 to the x. All right, so again, we got our decay factor is 1/2. Why do I call it decay factor? Because it's less than 1, right? When b is between 0 and 1, it's a decay factor. So now when I plug in x, if I do f of -2, right, what's 1/2 to the -2nd? Yeah, that means take the reciprocal. So you take the reciprocal 1/2 and you get 2. So it's 2 squared, which is 4. Now these I'm just going to multiply by 1/2 every time. So that's 2, that's 1, that's 1/2, and that's 1/4. All right, so if I plot these numbers, -2, 4, -1, 2, 0, 1, 1/2, 1/4, we're going to get this function, which looks very much like the other one, but now it's a decay function. So it's just my end behaviors are flipping. Right? And again, I have my asymptote. Again, this can never be negative. It never actually can't be anything less than or equal to 0. All right, so there's my decay function. Again, my end behaviors. Now my end behaviors as x approaches negative infinity. So the left end behavior. Now this one's going up forever. So now y is going to approach positive infinity. And then my right end behavior now is being controlled by the asymptote. So as x approaches positive infinity, right, it's going to approach the asymptote, which is at 0. So y approaches 0. My domain is still all real numbers. Right? For an exponential function, that's what it's always going to be. All right. You know, when we start throwing real life situations, there may not be negative time, but for now, if you're just graphing a generic function with no context, the domain will always be all real numbers. And my range here is the same as before. It never goes below 0. So the smallest value is 0. The biggest value is infinity. And they're both in parentheses because, again, it never actually equals 0. All right, so now your turn. Okay, you're going to answer these questions in the Ed puzzle. All right, so we're looking at a graph. Okay, it's f of x equals 3 to the x. All right, so I'm going to ask you guys to answer the following questions. All right, so the first one, is the function exponential growth or decay? And so since b is bigger than 1, and you can also tell by the graph it's increasing, this is a growth function. So what is the growth decay factor? Well, we know it's growth now. Okay, what is the growth factor? All right, so that's your b, that's your base. Okay, so that is 3. All right, you can write b equals 3 or just pick 3 there. All right, so now we need to evaluate, so kind of like we're making a table of values. So what is f of -1? So when you plug in -1, what do you get? So f of -1 equals 3 to the -1st, which is 1/3. Right, and then f of 2, so you plug in 2, 3 squared, which is 9. So f of 2 is 9. Okay, question 4, what's the domain? All right, so you look at the graph, or since again, it's an exponential function, so the domain is all real numbers. Right, and the range, okay, well, the asymptote's at 0, so the graph never goes below 0, or never equals 0 either. So it's going to be 0 to infinity, both in brackets. Okay, so could a function be flipped and reflected? Could it be shifted over to the right? Could it be shifted up and down? All those are true. We will talk about A, H, and K during block 1.